In this lecture, we will discuss about the generating function for Gnx. So, at first we will show that Gnx is the coefficient of z to the power n in the expansion of e to the power x by 2 z minus 1 by z. Now, we know the expansion for the exponential function e to the power t. So, for e to the power t it is 1 plus t plus t square by 2 factorial plus t cube by 3 factorial in this way. So, e to the power xz by 2, that will be equal to, we will write xz by 2 in place of t. So, we will obtain equation number 1. Similarly, the expansion of e to the power minus x by 2z. So, in this case we will put minus x by 2z in place of t. Then we will obtain equation number 2. Now, to get the series for e to the power x by 2 into z minus 1 by z, we will multiply equation number 1 with equation number 2. So, after multiplication we are obtaining this multiplication between these two series. So, if we multiply these two series, then we will have the expansion for e to the power x by 2 into z minus 1 by z. Now, at first we look at the fact that what is the coefficient of z to the power n in this product, that is in equation number 3, what will be the coefficient of z to the power n. So, how to find that? Now, you look at the first term, that is in the third bracket this series. So, in this series you see, if we look at term by terms, then this is in the first term, that is z to the power 0, then z to the power 1, then z to the power 2, then z to the power 3 and so on. Now, you see that for z to the power 1, outside we can write that is 1 by 1 factorial and it is x by 2 to the power 1. For z to the power 2, the coefficient is 1 by 2 factorial x by 2 whole square. The coefficient of z to the power 3 is 1 by 3 factorial x by 2 to the power 3. So, in this series, the coefficient of z to the power n will be 1 by n factorial x by 2 to the power n. Now, when this coefficient will be multiplied by 1, so in that case, after the multiplication, the coefficient of z to the power n will be 1 by n factorial x by 2 to the power n. But apart from this, we will again find the coefficient of z to the power n, because for the next term, that is the term just after the z to the power n, the power of z will be z to the power n plus 1. So, when z to the power n plus 1 will be multiplied with the next term here, then it will be z to the power n, because you see in the denominator there is z. So, in this case, that is when that n plus 1th term of this series, when it will be multiplied with the second term, then we will again obtain the coefficient of z to the power n. So, what will be the value of that coefficient? This will be 1 by n plus 1 factorial, just next term. So, 1 by n plus 1 factorial x by 2 to the power n plus 1 into x, because there is x in the second term. So, x by 2 to the power n plus 1 into x, that means x by 2 to the power n plus 2, and with a negative sign, because you see in the second term there is a negative sign. And just after this term, that is this term, so that will be 1 by n plus 2 factorial x by 2 to the power n plus 2, and that will be multiplied with this term. So, therefore, it will be x by 2 to the power n plus 4 and 1 by n plus 2 factorial. So, in this way, we will obtain the coefficient of z to the power n after multiplication between these two series. So these are the different terms we are obtaining. Now if we look at carefully, this series is actually the expansion of Gnx that we have already discussed in our earlier lectures. So the point is that you have to look at very carefully at this sentence, that is the coefficient of z to the power n in this series, that is coefficient of z to the power n for this series is Jnx. Similarly, coefficient of z to the power minus n in this series will be g of minus nx. Therefore, this series can be written in this way: j0 plus z into j1 plus z square into j2 plus z cube into j3 in this way, plus z to the power minus 1 j minus 1 plus z to the power minus 2 j minus 2 in this way. Why we are writing? Because of this fact, that is, for this series, for this exponential series, the coefficient of z to the power n is jn. This series can be expanded in terms of z to the power n, because you see that every term is some powers of z. So this series can be expanded in powers of z to the power n. But Jnx is the coefficient of z to the power n, and j minus nx is the coefficient of z to the power minus n. Therefore, as this series can be expanded in the powers of z, and z to the power n is the Jnx is the coefficient of z to the power n, and j minus nx is the coefficient of z to the power minus n. Therefore, we can write the expansion of this exponential series in this way, that means in this summation form, that is z to the power n Jnx, where n equal to minus infinity to n equal to plus infinity. Now there is a corollary for this derivation. You see the fact, that is the coefficient of z to the power n is Jnx. Therefore, the coefficient of z to the power 0, if we put n equal to 0 here, and if you put n equal to 0 in this series, then you will obtain value of the j0x. So j0x will be this series when n will be 0. So that means j0 is equal to 1 minus x square by 2 square plus x to the power 4 by 2 square 4 square in this way. So you can obtain the series for j0x from this equation if we put n is equal to 0 in this equation. Now we will discuss about trigonometric expansion involving Bessel functions. So this series can be expanded in powers of z. We have already established that, is this series can be written as j0 plus z into j1 plus z square j2 plus z cube j3. In this way, z to the power minus 1 j minus 1, z to the power minus 2 j minus 2. In this way, this is equation number 1. Now let us put z is equal to e to the power I theta in equation number 1. So left hand side will be e to the power x by 2 e to the power I theta minus of e to the power minus I theta, and on the right hand side you have to put z is equal to e to the power I theta. So z to the power minus 1 will be e to the power minus I theta. Now we will use one expression, that is we know e to the power I theta minus e to the power minus I theta by 2i is equal to sin theta. And we will use another expression, that is j of minus n, that can be written as minus 1 to the power n jn. We have also established this fact in earlier lectures, that is j of minus n, and that can be written as minus 1 to the power n jn. So here j of minus 1 term, you have to replace this term in this way, that is j of minus 1 will be minus 1 to the power 1 j1. j of minus 2 equal to minus 1 to the power 2 j2. So in this way we have replaced these j of minus n terms in for j n terms, that is we have written j1 in place of j minus 1. We have replaced j2 for j minus 2 in this way by using this expression, that is j of minus n is equal to minus 1 to the power n jn. then we are obtaining this expression, and the left hand side has been written using this equation. That is, for left hand side we have written e to the power ix sin theta. This is the left hand side and this is the right hand side. Now we know that e to the power I theta is equal to cos theta plus I sin theta. So using this formula, the left hand side we are writing in this way, that is cos of x sin theta plus I sin x sin theta. And for the right hand side, what we have done, you see that for example here j1 e to the power I theta and there is j1 e to the power minus I theta. So we can take j1 common and we can write e to the power I theta minus e to the power minus sin theta. And for the other terms also, for example j2 e to the power 2 I theta, here j2 e to the power minus 2 I theta. So we have taken j2 common. So we are writing right hand side using this type of equation. So for the right hand side, what we can do, we will again use that formula, that is e to the power I theta minus e to the power minus I theta by 2i is equal to sin theta. Using that formula, we can write, that is j1 e to the power I theta minus of e to the power minus I theta, that is 2i sin theta. So j1 into 2i sin theta, similarly j2 into 2 cos 2 theta. For plus term, that will be cos 2 theta. Again for minus term, 2i sin 3 theta, and so on. So in this way, right hand side can be simplified. Now what we will do, we will equate the real and imaginary parts from this equation. So equating real and imaginary parts, we can write that cos of x sin theta is equal to j0 plus 2j2 cos 2 theta plus 2j4 cos 4 theta, and sin of x sin theta is equal to 2j1 sin theta plus 2j3 sin 3 theta plus 2j5 sin 5 theta, and so on. If we put theta equal to pi by 2 minus alpha in equation 2 and 3, in that case we will obtain cos of x cos alpha, because you are putting x is equal to pi by 2 minus alpha. So sin theta will be cos alpha, and here also sin theta will be cos alpha. So cos of x cos alpha will be like this, j0 minus 2 j2 cos 2 alpha plus 2 j4 cos 4 alpha, and so on. And these equations are very important, because from these equations we can show some other types of derivation. For example, you just look at this example, that we have to show that cos x is equal to j0 minus 2j2 plus 2j4 and so on. Sin x is equal to 2j1 minus 2j3 plus 2j5 and so on. That is, here we have to show that cos series and sin series, they can be written in terms of the Bessel function. This is a very important problem. So we will start from equation 2 and 3 here. Just we have written these equation 2 and 3 from here to here. That is, this is the first equation and this is the second equation. Now you see that here the left hand side is only cos x and sin x, and here the left hand side has been written in terms of cos of x sin theta, sin of x sin theta. So if we put theta is equal to pi by 2, then here only x will be there in the first bracket, and here also. So just we have to put theta is equal to pi by 2 in these equations. So then we will obtain that cos series and sin series, and we can show that this cosine function and sine function can be expanded in terms of the Bessel functions. So we have proved this fact. Now suppose we have to show that x sin x is equal to 2 into 2 square j2 minus 4 square j4 and so on, and x cos x is equal to 2 into 1 square j1 minus 3 square j3 plus 5 square j5 and so on. So at first we use this formula again, that is we have written here formula 1 and 2. Now what we have to do, suppose we are starting from equation 1. So at first we will differentiate this equation with respect to theta. So if we differentiate with respect to theta, then what we will obtain, this is cos theta term. So for cos theta, this is minus sin theta, minus sin of x sin theta. Then you have to differentiate, that is inside the first bracket term, that is x sin theta. So for x sin theta, it will be x cos theta, as you are differentiating with respect to theta. And in the right hand side, they have also been differentiated with respect to theta. So this is equation 3 after differentiation with respect to theta. Again we have to differentiate with respect to theta to equation 3. So if we again differentiate equation 3 with respect to theta, then that will be the left hand side. So this is the form of the left hand side, and you can differentiate it by standard rule. So this is the differentiation for the uh, for this expression of the left hand side. For example, suppose this is sine of x sine theta, this is the first term, and this is the second term. So here first term is constant, differentiation of the second term is minus x sine theta, and here you have kept minus sine x sine theta constant, and you have to differentiate x cos theta with respect to theta. So that will be minus x sine theta. So in this way, what we can do, you can differentiate with respect to theta. Now for the right hand side also you have to differentiate with respect to theta. So thereby you will obtain the equation number 4. Now what we have to do, you have to put theta is equal to pi by 2 in this equation. So if we put theta is equal to pi by 2, then what will happen, that is all the sin theta term will be 1 because sin pi by 2 is equal to 1, but cos pi by 2 is equal to 0. You see in the second term there is a term cos theta, that means cos pi by 2, means second term is 0. So only you will obtain the first term, and from first term the result will be x sin x. You see the result is x sin x because all sin theta term will be 1. So ultimately minus and minus, and that will be plus sign. So ultimately you will obtain x sin x, and for the right hand side you will obtain 8j2 minus 32j4 in this way. So this series can be written rearranged in this way, that is, suppose if you take 2 common, then first term will be 2 square into j2, next term will be 4 square into j4, then 6 square into j6, and so on. So x sin x can be written in this series. And similarly from the second equation, actually we have started from equation number 1, and we have derived this sine series. But instead of 1, if we have started from equation number 2, then just with the similar process, that is, we have to at first differentiate with respect to theta, then again you have to differentiate with respect to theta, and you have to put theta is equal to pi by 2. Then by the similar process you can show that x cos x is equal to 2 into 1 square j1 minus 3 square j3 plus 5 to the power 5 square j5, and so on. So in this way we can derive those equation. Another important equation, that is, suppose we have to show that j0 square plus 2j1 square plus 2j2 square they are 1. So how to show that? So we will start from the equation that is cos of x sin theta, that is just we will use these two equation again. These equations are very important, you have to memorize that. So we have written equation, this is the first equation and this is the next equation. Now we will square this equation. We will square this equation and integrate with respect to theta between the limits 0 and pi. Squaring 1, at first we will square it, then we will integrate it with respect to theta, and limits will be 0 to pi. So the right hand side will be 0 to pi integration cos square x sin theta d theta, and for the left side you think that square of this series will be at first square of the individual term. For example, j0 square, next is 2 square into j2 square into cos square 2 theta, and so on. That is square of the individual term, and thereafter that is multiplication between different terms. That is, for example, multiplication between first two terms, then this term and this term, and so on. That is another values will be multiplication between the individual terms. Now we will use some results of the integration. For example, you see that if you integrate 0 to pi, limit is 0 to pi, and 2 sin square n theta d theta, so value of this integration is pi. Similarly, 0 to pi 2 cos square n theta d theta, value of this integration is again pi. But suppose if integration is 0 to pi 2 sine n theta sine m theta d theta for any value of m and n, if it is if the limit is between 0 to pi, that will be 0. Similarly for 2 cos n theta cos m theta d theta 0 to pi, that is also 0. Now you see that suppose we are using equation 1. So when there will be multiplication between the individual term, so there may be the structure of the multiplication term is like this. So suppose there are two cosine terms for any values of m and n. There may be one term also, suppose n is equal to 0, but whatever it is, when you integrate between 0 to pi, that will give you 0. So only square terms will exist, because when we are accounting for the individual square terms, integration of 0 to pi 2 cos square n theta d theta is equal to pi, that is not 0. So using these results of the integration, if we use these results in the left hand side, then we will see that for the left hand side we are obtaining this series, that is j0 square pi plus 2 j2 square pi plus 2 j4 square pi and so on. And this is the right hand side. And similarly, if we square the equation number 2 and integrate, then from the equation number 2 we will obtain 2j1 square pi plus 2j3 square pi plus 2j5 square pi, and in the right hand side 0 to pi sine square x sine theta d theta. Now we will add this equation, that is equation 3 and 4. If we add this equation 3 and 4, in one side we will obtain this one, that is 0 to pi cos square x sin theta d theta plus 0 to pi sin square x sin theta d theta. When we add them, we know that cos square theta plus sin square theta is equal to 1. So ultimately we will obtain pi only. And in another side we will obtain, that is if we add them up, then we can take pi common, and inside will be j0 square 2j1 square plus 2j2 square and so on. So pi will cancel out. Ultimately we will obtain j0 square plus 2j1 square plus 2j2 square plus 2j3 square and so on, that is equal to 1. So in this way we can prove this. So this is what about the concepts of Bessel function. I request all the students to go through the textbook of Das and Verma for further understanding, and I will also request to solve the exercise problems given in this book. And thank you all for listening the lecture.